Ladies and gentlemen, I am Mudie Mafojani. I will be doing momentum and impulse, which is a grade 12 topic, which you had done with your grade 12 learners. Just a quickly reminder that this topic for the current grade 12s, it is not a new, it's a new topic, I'm sorry, but it's a topic that has been there. And for the teacher that was teaching the topic, you are experienced with the topic. But very quickly, let's look at the preparation part of momentum and impulse. What are the key aspects that we need to take into as we teach, as we revise with our learners? You know, in physical sciences, we've got documents that guides the teaching and learning of physical sciences. This first part of the presentation is really going to look at how best we can come up with a well-prepared lesson for the learners. And very important and very key, remember, we are teaching learners at different levels of performance. So we need to make sure that our approach, our methodology in terms of teaching and learning in physical sciences accommodates all the levels of the learners in your class. Right? Let us enjoy momentum and impulse. As I explained, the first part is the preparation that we've been going around together with subject advisors in our startup workshops to say we need to prepare our lessons very, very well. And we need to use the examinable content document, the grade 12 one, which is out. We really need to use the CAPS, which is a very important document. That's where teaching starts. We've got the National Diagnostic Report. It's also very, very key. We've got the item error analysis. These are the very key important documents that informs our preparation for any lesson. And I want to say to you and motivate you and encourage you that these documents, they make a lesson worth to be listened to. Okay, let's look into the momentum and impulse. I'm going to start from the examinable content and work schedule. What does it say? And I want to believe at this stage you are familiar with the two documents and are very, very key when it comes to the preparation. Number one, this section must be read in conjunction with the CAPS, which is on page 99 to 101. That's where we get a detailed point that we need to teach when we teach momentum and impulse. And this statement specifically, I took it out from the examinable content document. What does this mean to us, ladies and gentlemen? Simply means that all these documents that I mentioned earlier on are really complementing each other. There is no way that a comprehensive and a detailed lesson can be done by a teacher without these documents. So what does the examinable content says with this topic specifically? The learners need to define momentum as the product of an object's mass and its velocity. You know, the nice thing, the most important thing about the examinable content document, it also gives us the acceptable definitions. So this is just not a document, but it's a working document, and all learners must be able to know the definitions as stated in the examinable content document. On momentum only, they need to describe the linear momentum of an object as a vector quantity with the same direction as the velocity of the object, which is mostly, you will see when I go to the basic lesson of momentum and impulse, learners mostly do not mention direction if they are required to do so. So emphasize that momentum is a vector quantity and it is in the same direction as the velocity of the object. And under momentum as well, the learners need to calculate, be able to calculate the momentum of a moving object using P equals to mv. Let me just explain a little bit on this formulae. I know quite a number of teachers has asked me that, do we really need to put arrows on top of P and on top of V to show that the vector nature of momentum? Right. Look at the examinable content document. On the data sheet, there are no arrows there. So a learner who writes P equals to mv won't be penalized, as much as the learner who decides to put arrows, that the learner will not be penalized. So I'm busy addressing the key points as you treat momentum, as you introduce momentum. The other point is describe the vector nature of momentum, and very important, and illustrate it with some simple examples. You know, the biggest mistake that we do as teachers, we do not start at the basic foundation. We start giving our learners challenging questions, which is not a problem, but make sure that the basics of that particular topic or aspect are being taught to your learners. Very important, your learners, after you had taught them, must be able to draw vector diagrams to illustrate, that's very important, the relationship between the initial momentum, the final momentum, and the change in momentum for each of the above examples. For each of the above examples. Which examples? The vector nature of momentum, as you illustrate them with some simple examples. Ladies and gentlemen, as we continue, as you engage in this topic, the second part, you had introduced momentum, right? Now, you have to relate momentum with Newton's second law. And this topic in particular is being treated in grade 11. So, very important. In grade 11, ensure that the second law is taught to the best of your ability, because the learners need that to be able to express momentum in terms of Newton's second law. Now, very important, what are the key points in this subheading? Is learners must be able to state Newton's second law of motion in terms of what? Of momentum. And what does it say? It simply says the resultant or the net force acting on an object is equal to the rate of change of momentum of the object in the direction of the resultant or net force. You know, learners, when they state laws, they normally have the ability of leaving out key words. We talk about here the resultant of the net force. And you know, at the end of this law, it says in the direction, you know, of what? of the resultant or the net force and not the applied force. You know, this is the law. And learners needs to be able to state. So, as you mark your learners, as you give your learners activities, be very consistent and very strict in terms of the key words. And what does it say? It is equal to what? The rate of change of momentum. Right. The second sub-bullet in this subtopic within momentum and impulse. Remember, the bigger topic is momentum and impulse. Express Newton's second law of motion in symbols. Look, I always say, physics laws and principles are directly talking to the formulae. Now you look at that formulae, it says F net. Or the learner can say F res equals to the change in P divided by the change in T. And what does the law say? It simply says the resultant net force acting on an object is equal to the what? The rate of change. And when we start saying the rate of change, it means there's time implication. And that you see there on the formulae. So, ladies and gentlemen, as you teach your learners, the law and the formulae, show them how the two are directly linked together. It is in the law that you get the formulae. It is in the formulae that you can state the law. So when either of them is not conversed with in the learner's mind, there is no way that the application part could be possible. Right. The other bullet on this heading, Newton's second law of motion in terms of momentum. When you teach your learners, they must be able to calculate the change in momentum when a resultant or a net force acts on an object and its velocity. And here we've got particular conditions where they have to calculate and when they have to calculate the change in momentum. Ladies and gentlemen, our terms, let us be very clear when we talk to the learners. As an applied force, it depends on the scenario, cannot, under normal circumstances, be a resultant force. The moment we talk about a resultant or the net force, it means more than one force. It's acting on the particular object. So, please explain these terms to your learners as you teach these key words, because they are very, very key in describing terms in physical sciences. Now, when do they calculate the change in momentum? Number one, when the resultant net force acts on an object and its velocity increases in the direction of motion. And the example is a second stage rocket engine fires. Let me give you a tip. Ensure that as you teach all these bullets, you teach them so well. Each bullet, there is an activity addressing the particular bullet. And once you do that, ladies and gentlemen, I bet, I'm telling you, I'm confident that the whole topic would have been taught very, very as it is supposed to be taught. The second condition, when a resultant force acts on an object and its velocity does what? Decreases. And what I like about the examinable content, it gives you examples. So, as you are sitting with those resources, your textbooks, whatever resource available, look for examples like when the brakes are applied. This is one thing very important about CAPS. It's very clear. is very prescriptive and very simple. And the last one, when a resultant or net force acts on an object and its velocity reverses its direction of motion. What is an example to that? A soccer ball kicked back in the direction it came from. These are just the minimum examples. Exhaust these specific cases as far as possible with your learners. I normally say, you treat all these situations, every possible scenario, give it to your learners, but very important, it should be in line with, for an example, when its velocity increases in the direction of motion. All right, right. Let's continue as we exhaust the examinable content document and the work schedule. The second subtopic here is impulse. Define impulse as the product, right, of the resultant or net force acting on an object and the time the resultant or net force acts on the object. This is the definition of an impulse. This is the definition of an impulse. So, very key, very important. The grade 12 examinable content document serves many purposes. Number one, it's a document for you to start preparing. In that document, we have acceptable definitions. So, this is a working document, a very important document. Now, the second bullet on impulse. The first one was momentum. The second one was relative momentum in terms of Newton's second law. Now, we are exhausting the impulse. They must deduce the impulse momentum theorem. You and I know that F net, the change in T, equals to the mass of an object multiplied by the change in the velocity of that velocity. And go back to the first point. What does it say? Impulse as the product, right, of the resultant force acting on an object and the time the resultant or net force acts on the object. And that is the impulse momentum theorem. F net, the change in T, equals to M, the change in V, where the mass, M is the mass of an object. Right. The third bullet, use the impulse momentum theory. Now, you know, it is the definition, the formulae, and the application. I guarantee you where I'm sitting here, if your learners cannot define impulse, it will be challenging for them. I'm not saying difficult. Challenging for them to deduce the impulse momentum theorem. And if they are conversant or not conversant with the impulse momentum theorem, it will be very challenging to apply, all right, the impulse momentum theorem to calculate the what? That's key, ladies and gentlemen. The force exerted, the time for which the force is applied, and lastly, and the change in momentum for a variety that's key for a variety of situations involving the what? The motion of an object in one dimension. You know, one important aspect of the examinable content document, it clearly tells you where to go, what to do, examples to focus, and those are just the minimum. What you have to do, you need to expand on that, beginning from the foundation, the lowest level of thinking, and to the next one, to the next one. Up we take those learners to high order thinking questions. That's how teaching is very interesting and learning is very interesting. Now, explain. This is the application now. How the concept, all right, of impulse applies to safety considerations in everyday life. For an example, airbags, seat belts, and arrestor belts. These are the key points in terms of the impulse. Right. Now, the conservation of momentum and elastic and inelastic collisions. Ladies and gentlemen, explain what is meant by a closed or an isolated system in physics, all right? Which is a system on which the resultant or the net force is zero. Very interesting. This is very interesting and very important. Explain what is meant by a closed or an isolated system in physics. This is the definition. A closed or an isolated system excludes external forces that originate outside the colliding bodies. An example, friction. Only internal forces, right? For an example, contact forces between the colliding objects are considered between the objects, which all these objects together, it's a system. And that system is a closed system when no external forces originating outside the colliding bodies, those colliding objects are considered. And I want to believe at this stage you did the experiment that verifies this principle of conservation of momentum. And I hope your learners enjoyed to see a closed and an isolated system. Yes, indeed, in a closed and in an isolated system, momentum is observed, is conserved. It's conserved. Sorry for that. Right. Your learners must be able to state the principle of conservation of linear momentum, which simply states the total linear momentum of a closed system remains what? Constant or is conserved. More often, learners leave keywords like the total and the closed system. So, when you give activities, ask your learners to state the principle, to state the laws, and be very consistent. When a learner leaves out keywords, then I bet you that is not the principle, if a word is being left out. Okay. very important. Apply the conservation of momentum to the collision of two objects moving in one dimension and where along a straight line with the aid of an appropriate sign convention. You taught them the principle. You did an experiment to verify the principle. Now it is the application. And this is where physics is very interesting. This is where the physics is very interesting. The application. And let me just take you back. Before the application, they need to know tense. They need to know conditions. And now they apply. That is the rhythm. This is how it works in physics. There are two types of collisions. Elastic collision and inelastic collision. Teach them to distinguish, how to distinguish these by calculation. All right. This is very important. That was the first part as you prepare, as you plan around teaching the topic. Right. Now, the second step, the prior knowledge. Before you teach, what is it that my learners should have? The prior knowledge is very key, ladies and gentlemen. And like I said earlier on, the diagnostic report is a very important document that outlines the common mistakes that our learners are doing. So, and this is the message that we preached during our startup workshops, to say, infuse the diagnostic report in your daily teaching. And this is how you will do it. You can do it. It's not a cut in stone, but you need to mention. It's true. It's different learners. But the challenge is it's the same mistake done by different learners. So it's very key that you first present the common mistakes. As they normally say, forewarned is forearmed and prevention is better than cure. All right. What is the prior knowledge? The use of equations of motion in solving problems dealing with momentum. And where is this done? Ladies and gentlemen, grade 10 and 11. This is the most important thing about CAPS. You know, the flow of topics, making a bigger picture, flowing very and making sense. Equations of motion are done in grade 10, in the fourth term. Grade 11, we deal with equations of motion, you know. So, if you are a group of teachers in different grades, make sure that these aspects are taught. And it is a bonus when you teach from grade 10 to grade 12. You are building those learners from grade 10 up to grade 12. Right. This one in particular comes from the diagnostic report. Momentum is a vector quantity. What needs to be done? Emphasis must be placed on the choice of direction. when solving conservation of momentum problems. Ladies and gentlemen, emphasize this aspect. Because, you know, learners, there are two things that are happening. They forget to choose direction, and somewhere in the substitution, we realize there's a choice of direction. But as they further calculate, learners are unable to carry their choice of direction further. And when the question says calculate the velocity, velocity is a vector, ladies and gentlemen. And they need to further interpret what? The direction. All right. So, this is very key. This is very important. Learners need to be able to state the magnitude of a vector. And when the question says the magnitude, it means we need the magnitude, the size, and to specify its direction when given the vector quantity. Ladies and gentlemen, please verify this as you teach your learners. And the only way for you to emphasize this aspect is when you mark your learners' daily tasks. Quality daily tasks. Daily tasks that are weighed in terms of Bloom's taxonomy. Daily tasks that talks to the topic. All right. This is very important. Learners also need to know and understand vector equations within the confines of the curriculum. You know what they do? They're given the data sheet. And what they do, they pick and choose. Guide your learners with this, in this regard. It's very key, very important. Very key, very important. Learners must be exposed to different applications of conservation of momentum involving both collisions and explosions. And this is rightfully stated in the what? In the grade 12 examinable content document and the work schedule. All right. The teaching of momentum must be integrated with Newton's laws. The grade 12 examinable content document is very clear. And from previous slides, you had seen learners need to interpret Newton's second law in terms of momentum. And not only Newton's law, Newton's second law, all Newton's second laws. This is where our learners are still lacking. So, ladies and gentlemen, you are the driver of that particular class. Ensure that all these bullets are comprehensively and in detail with quality for that matter are being covered. All right. More explanation type questions should be given to learners to work out in class. Question 4.4.2 in November 2013 and 4.4.1. Learners had to explain, given the scenario, the boy and the package, you remember. When you look at the diagnostic report, the moderator's reports, look at the performance of the Free State learners. Our learners cannot give explanation type, cannot answer explanation type questions. And they can only do that, ladies and gentlemen, when they are exposed. And not just exposure, but more exposure. Meaning, your daily tasks, starting from your simple homeworks, must have all the levels of Bloom's taxonomy. The homeworks must address, all right, all type of questions that learners will be asked at the end of the year. And the examinable content document clearly specifies the percentage, the type of questions that learners will be expected to answer, whereby explanation type questions is not an option, but they are going to be asked on this. For your information, let's teach our learners to answer open-ended questions. It's coming, ladies and gentlemen, because you look at the previous question papers. Most questions, they led learners to the answer. But from the reports from external moderators nationally and, from other countries, the report is that in South Africa, we are leading learners to the answers. So be careful this year. Open-ended type questions that, like the ones we saw in 2008, are heavily coming back, ladies and gentlemen. For an example, use the physics principle to explain why. And that question does not say use Newton's second law. No. The physics principle. All right. So, this is very important to mention because they will be answering such type of questions. Now, let's look at momentum and impulse, the flow diagram. Under momentum, there are three aspects. They must define momentum, describe linear momentum. These words, define, describe, explain to your learners. Define, describe, okay? Calculate momentum of a moving object. I remember in one question, the question said, determine. And the learners started calculating. So these words, ladies and gentlemen, are key, are very important to explain to your learners the difference in the definition, the difference in the description. Right? Right? As we continue with our flow diagram, you are now taking small and big pieces of the puzzles and making a bigger picture now. You are now driving your point as a teacher now. They must describe, all right, the vector nature. Draw vector diagrams to illustrate the relationship between the initial momentum, the final momentum, and the change in momentum for each of the above examples. This is very, very important. You are now driving your point home. You can either start with a flow diagram as you start your lesson, but the most important thing, how you introduce the topic. You need to provoke that curiosity of your learners to want to know more on that specific, specific topic. I think that's the most important, interesting, triggering factor for to trick the learner's curiosity into listening to you again. All right. Now, calculate the momentum. It all goes down under calculate momentum. They need to, Newton's second law of motion, stated in terms of momentum. They need to express it as they stated. And F net equals to the change in P over the change in T. I like it. And then they need to calculate, right, the change in momentum in this particular last balloon, and you refer to the examinable content document. Those three, when it decreases, those three aspects, when velocity decreases, it increases. You know, those three scenarios. Make sure that you cover each and every sub-bullet with quality activities, which are all in the resources that you have. Right? Right? Impulse. Define impulse, simple as that. Deduce the impulse momentum theorem and the application. This is very important. Very, very key and very important. Explain how the concept of impulse applies to safety considerations in everyday life. For an example, airbags, seat belts, and arrestor belts. You know, when you have a flow diagram, your learners are very clear where you are taking them to. All right. You bring them on board. You said, this is where we are going. And to arrive there, these are the station points we need to have covered when we say we had completely covered impulse. All right. The conservation of momentum and elastic and inelastic collision. What needs to be covered? First and foremost, they must know what is meant by a closed and an isolated system. Number two, they must be able to state the principle of conservation of linear momentum. They must be able to apply the conservation of momentum to the collisions of two objects moving in one, ladies and gentlemen, in one dimension. And what is that? Along a straight line. Distinguish between elastic collisions and inelastic collisions by calculation. You know, last year we had a question in March, I think in June as well, where the learners had, through calculation, to prove whether the collision is elastic or inelastic. And I remember the question was, the answer was inelastic. But the moment the learner starts saying the change in EK before equals the change in EK after, the learner had concluded, and it's contradicting to what the learner is saying. And then after they calculate, at the last step they realize, no. The kinetic energy is not the same. Then they start saying it is inelastic. They start with a wrong assumption. Unless they say assume, and then they start proving. And at the end, they start saying kinetic energy before collision is not equal to the kinetic energy after the collision. Therefore, the collision is inelastic. And one thing that differentiates these two collisions, it's only one thing, kinetic energy. Inelastic collision is conserved, both momentum and kinetic energy. But in inelastic, it's only momentum. All right. This marks the end of our first part of the presentation. And we are going to look at the basic lesson of momentum and impulse, and all what I talked about in the previous session. I'm going to try and show you the application, especially where I said after each and every bullet, ensure that you give learner the activity, and not just an activity for the sake of an activity. And maybe, ladies and gentlemen, we need to refrain from teaching and assessing after. The simple principle is you assess, you teach, and assess. Remember, in one of the slides, I talked about prior knowledge. And how do you determine that your learners had done equations of motion? How do you determine that your learners understand Newton's second law? Is by first giving your learners a baseline assessment. In other words, the approach is you move from the known to the unknown. That makes it easier. Even in life, when you move from the known to the unknown, the journey makes it worth to be traveled. And that is the principle of teaching. For each topic, let's check the prior knowledge. And how do we do that? By designing a quality, all right, quality assessment task. Be it a homework, be it a classwork, be it an informal test. And very important, all the types of questions need to be asked at any level, at any daily task. This is very important. And for this part of the session, colleagues, thank you very much. And then let's meet after 10 minutes. Thank you very much. Ladies and gentlemen, welcome back to Momentum and Impulse. The first part was more on showing you how to prepare a topic. I know you are experienced teachers, but we more often than not forget documents that assist us as physical sciences teachers to make a very sound lesson. So the main important thing in the first session was to show you how do we use the examinable content document. It's not just a document that prescribes the examinable content, but it's a teaching tool. I had shown you a part of the work schedule, whereby now what are the important bullets that you need to have covered when you say, I had taught momentum and impulse. I had also shown you the importance of the role played, very important, by the National Diagnostic Report, which I'm certain where I'm sitting that all the teachers in the Free State were given the document on a CD, the electronic copy. And the fourth point I highlighted is when you start preparing. You know, there's a difference between preparing and planning. When you prepare, you sit down and study the topic. Irrespective how many years you've been teaching that, certainly you will forever find interesting facts of that particular topic. And remember, as teachers, we are dealing with different learners. So, the same approach for 2013, definitely it might not work because you are dealing with different learners. So, it's very key, it's very important that you give the preparation the best that you can, and so that you are confidently saying, I had taught and no doubts, I had given my learners, I had covered all the bullets. And the other leg that I would want to encourage you as physical sciences teachers, you need to begin to prepare for the daily tasks as well. It's not a task because you are stuck, you don't know what to do. No, it's a feedback for you as a teacher to say, my learners still cannot state the principle of conservation of momentum. You know, that is a feedback that you get when you mark your learners and you realize they miss out the key important words, which is what we normally experience as we mark the learners' answers at the end of the year. So this is very key and very important that you assess, teach, and assess. Right. I have a very simple momentum lesson, and feel free to modify it, but it starts very, very simple. Ladies and gentlemen, let me reiterate again. Every class has learners operating at different levels. A one-size approach fits all, it will not work in a classroom. You need to accommodate your level 1s, your level 4, 5, 6, and your level 7s. Right. Now, this lesson starts with the definition of momentum, where the learners has to complete the missing words, right? This is a scenario, and when you look at this, it touches on the basics. The symbol, the definition, you know, there is a car moving in that direction to the right from my frame of reference, right? Now, what is happening? The car has got a mass of 2,000 kilograms and the velocity of 16 meters per second to the right. All right. Remember, at this stage, you had introduced the topic, and you are now continuing and coming with practical scenarios. Now, momentum, its symbol is P, and the definition of momentum is the product of the mass and velocity of a moving body. All right. In this particular instance, we are talking about the car. The formula for momentum is P equals to the mass of an object multiplied by the velocity that the object travels. And from the scenario given, mass is 2000 kilograms and the velocity is 16 meters per second. And your learners, what they do, just say, calculate the momentum. You start very simple. Ne? You start very simple. They are given the mass. They are given the velocity. They just, they know the formula, very important, and the symbol, very important. Ne? And from the definition, the momentum is the product of the mass and the velocity. And there it stands. That's the product. 2000 multiplied by 16. That gives us 32,000 kilogram per meters per second. To the what? To the right. Remember, momentum is a what? Is a vector. And the units for momentum is kilogram meters per second. Most learners, they forget to write the units. And very interesting, we expect learners only at the end, at the final answer, to write down the units. And an answer without a unit, even if it's correct, even if it's 32,000, you do not mark the learner right. Okay. Since velocity is a vector quantity, momentum is a vector quantity as well. Now, we are now bringing in Newton's second law. And to integrate Newton's second law into momentum, they first need to know what is Newton's second law from grade 11. What you do, just a baseline assessment. All right. Newton's second law, you know, I said to you, definitions are playing a very critical and important role. All right. Right. Let's look at they need to complete the definition. They need to do a basic calculation, no? A basic calculation, all right. And then they need to give us units. That's very important. Meaning, the learner would know if we say F res, the resultant force or the net force equals to ma. What is its unit? What is the mass? Unit. What is the acceleration? These are the basic things. Whether be a level 1, let me be clear, a level 7, they need to know the basics. And you take these learners step by step to the point where you have to, which is high order thinking. And this is an object of mass. And there's a resultant force on that particular object, and the object, it experiences acceleration. And the mass of the object is 2,000 kilogram. Acceleration is 16 meters per second in 10 seconds. All right. Now, what is Newton's second law? If an object experiences, keywords and correct terms are important, a resultant or a net force, the object, all right, will accelerate in the direction of the force. But this is only the first part of the law. Remember, the acceleration of this object is inversely, all right, proportional to the what? To the mass of the object. And here, I just took the first part, where now I wanted to show you the first part and its relationship to the establishing Newton's second law. All right. All right. You start with the formula. There it states, if an object experiences a resultant net force, the object will accelerate in the direction of that force. So, we assume that, yes, there is the resultant force applied. In fact, there is the resultant force on the object that this object experiences, right? And the resultant force simply means more than one force is acting. And then there is the resultant force. They must be able to simply write down the formulae. F res stroke net equals to MA. Or F net equals to MA. Right? Now they plug in. They plug in the data. Mass is 2000 kilogram and the acceleration is 1.6 meters per second. What is the resultant force? 3,200 newtons to the right. Force is a what? Is a vector. All right. We measure resultant force in newtons, the mass in kilogram, acceleration in meters per second squared. These are just the basics for any topic. Right. Let's engage on this one. All right. Now, the applied resultant force, we now combine Newton's second law as per the below bullet and the momentum. The applied resultant force is equal to the rate, The change of momentum is different from the rate of change of momentum. Those are the specific terms, ladies and gentlemen, that you need to emphasize. And that this change is in the direction of the what? Of the resultant or the net force. Exactly what is in the law, it is expressed in the form of a formulae. You look at your furthest right. F net equals to the rate of change of momentum. And now we further unpack the change in momentum, which equals to the what? The momentum before and the initial momentum, and the final momentum minus the initial momentum. Divide by the change, all right? The change in time, not the time. This is derived from Newton's second law. The net force is directly proportional to the change in momentum. All right. Now, let's enjoy the impulse. There's an object, the resultant force, right? And then we have to complete, they have to complete impulse changes, blah, 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 blah. And then, you are touching on the basics, which I emphasized on. And here, sorry for that, should be the change in T. Very important, should be the change in T. You are touching on the basics so that when you go to the next level, you take your learners to the next level, they can play around with formulas. They know the formulas. They know their units. They can operate at a very simple basic level. And then you can move on. Right. Impulse is the product of the resultant force acting on an object and the time. The resultant or net force acts on the object. Ladies and gentlemen, it's very key. You need to explain. You need to describe to your learners the meaning of the definition. Is the product of the what? Resultant force acting on what? On an object and the time, the change in time. And the time the resultant or net force acts on the object. Right? Have your little demonstrations to make it easier for it to make it sense. I mean, make it sense to the learners. Okay. Impulse changes momentum. And then you now go to the formulae. The same thing that we did in the previous slide. F resultant or F net equals to ma. Acceleration is the change, the rate of change of velocity. And the change in velocity includes the final velocity and the initial velocity over a specific time. Very interesting. So, now we continue. Mass multiplied by the final velocity minus mass multiplied by the initial is what? Is the change in momentum. And what do we have on the left? We have the resultant force or the net force. And what do we draw? Impulse equals to the what? The change in what? In momentum. Right. Now, let's look at the momentum conservation. These are just examples on how you can introduce, all right, each subtopic. We have object A of 2 kilograms moving to the right at 5 meters per second. We have object B of 3 kilograms moving to the left. And to the left is taken as negative. And then they collide, and after collision, both A and B are moving in the A is moving in the opposite direction to the original direction, and B is still moving in its original direction to the left. Let me pause here and explain something. Ladies and gentlemen, when your learners are answering a question, and in the question it says the left, the right, the east, the west, the up or down, the north or south, when they answer, let them stick to the words that are being used. You see, here I said to the right. Ne? I said to the left. I can also say to the east, to the west. But if the east and the east or the left and the right is the one that is being used on the problem, let them answer or interpret direction in terms of what is in the statement. For an example, say it says to the east, and then they have to calculate the change in momentum, all right, or the velocity or whatever. And then the learner says A will move in the opposite direction. To what? Of motion. To what? You see? So it poses a problem. Let them be clear. They said to the east, and then it's now moving to the west. Let them say west in the opposite direction to the what? To what? Well, if they say B, to in the original direction of B, well, but for me, I wouldn't advise my learners for that. Let them stick to east, west, left, right, period. And this is just a simple demonstration. After performing that experiment of the principle of conservation of momentum, give the learners further a data collection and let them, manipulate the data and see what we did whilst we performed the experiment. It's here. Remember, learners have to calculate, proving whether it is the collision is elastic or inelastic. All right. Right? It states that the total linear momentum of an isolated system remains constant in both magnitude and direction. All right. Total momentum before the crash equals to total momentum after. That's very important. In symbolic form, the sum of the momentum before equals to the sum of the momentum after. And look, that is the formula. You plug in the data given. The left or the west is taken as negative. And minus 8 is approximate to minus 7.99. So the total momentum before the crash equals to the total momentum after the crash. All right. Change in momentum is 0. Change in momentum equals to the final momentum equals to the initial momentum. And the change in momentum is 0. All right. Now, they need to be able to differentiate between elastic and inelastic. It should be inelastic or non-elastic collision. All right. During the elastic, they combine on impact. They separate on impact during the inelastic. Collisions can either be elastic, and I said earlier on, energy is conserved, meaning no energy is lost. There was a question last year of vertical projectile motion. Learners had to explain why. They could say energy is not conserved, but they could not explain that the velocity that the ball hits the concrete floor is not the same as the velocity as it leaves. All right. Inelastic, kinetic energy is not conserved. Some is converted to heat, sound, and the unit for the energy is a joule. All right. Momentum is conserved in any collision between two objects, but kinetic energy is conserved only in a perfectly elastic collision. And remember the other condition, for us to observe the conservation of momentum, we need to have what? An isolated system. Now, let's look at this simple calculation. A 35 kilogram girl is standing near to the left. I said assess, teach and assess. Ne? You don't wait for Friday to give this learner the simple, straightforward calculation on the conservation of momentum. It says a 35 kilogram girl is standing near and to the left of a 43 kilogram boy on the frictionless surface of a frozen pond. The boy throws a 0.75 kilogram ice ball to the girl with a horizontal speed of 6.2 meters per second. Please look at this. We put the dot on top and -1 there. What are the velocities of the boy and the girl immediately after the girl catches the ice ball? You know, one thing that you need to encourage your learners, let them draw, visualize the scenario being given. Let them determine before and after. I've got a very good reason to that. In that question 4 of November 2013, the boy was throwing a package, and most learners were not aware that before the throwing, everything, the momentum is 0. We had values for the momentum before the throwing. So, encourage your learners to draw, or in any way, some sort of, having the scenario. What is really happening in this particular problem? Right. There is the gap of mass 35, and the boy is throwing that the ice ball. All right. And look, west is positive, and that is the mass of the ball. Now, for the boy, west is taken as positive. Before, this is the mass of the boy and the what? And the frozen pond. All right. And then after. All right. It's 0. And what happens? Our answer is negative 0.11 meters per second, which is 0.1 to the, remember the west is what? Is positive. Therefore, interpreting the answer. West is positive. So our answer is a negative answer, meaning that's the east. And same applies to the gap. Remember the sum here. The sum, and the answer is positive, meaning the velocity of the gale is the west, towards the west. All right. All right. The other problem, change in momentum and impulse. A 1 kilogram ball moving with a velocity of 5 meters per second to the right collides with a wall and bounces back with a velocity of 3 meters per second. If the collision takes 0.05 seconds, calculate the force exerted by what? By the wall on the ball. And that is a scenario. This is what happens before, and then we need the force. That acts over 0.05 seconds. Right? I think we need, what is key, we need the change in momentum. All right. Right. Now, the initial momentum of a 1 kilogram is 1, the mass multiplied by the velocity, and the final momentum of that 1 kilogram, the left is taken as negative. Momentum is minus 3 kilogram meters per second. And the change in momentum, the final momentum minus the initial momentum. Where the final momentum is what? Minus 8 kilogram meters per second. We interpret the minus. The change in P is equals to 8 kilogram to the left. All right. There we are. We haven't calculated the what? The force exerted by the wall on the what? On the ball. Impulse equals to what? The resultant force or the net force multiplied by the change in time, which equals to the change in P. We have the change in P there. Remember we calculated what? The change in P. And then we substitute. And this force exerted, it acts over 0.05. And the F net, it should be F net here. It's 8 divided by 0.05, 160 newtons. Simple. straight to the point, application, of changing momentum and impulse. All right. Simple, straight to the point. Okay. You start very, very simple. Right. Those were the activities that I wanted to show you, and a very simple lesson that I prepared for you. And my last words would be, may the good Lord give you all the strength as you teach your learners, and good luck in everything that you are doing. I know that teaching is not as easy as everyone thinks, but let's keep on doing the best that we can, and all the best, as I hope you will enjoy this. This is the most simplest lesson I had for you, and all the best in everything that you do. Thank you very much.